This is 9.5, continuing. This is part 3. So let's see. We're about to start example 6. Determine whether each series is convergent or divergent. If convergent, classify the series as absolutely or conditionally convergent. Alrighty. So pen. Oh, I forgot. There we go. Sorry. There's one little thing I forgot to do there to make my pen work. So let's just not doing anything for a second there. All right, so our first example is -1 to the n times n plus 1 divided by 2 power divided by 3 to the nth. Now, this is the first time we've had that kind of exponent. That's actually a quadratic exponent. And as we're about to see, that kind of throws some things out the window. If it's -1 to a linear exponent, unless I'm not thinking of something that should be obvious. No, it has to be 1n. Can't be 2n because then it's always even. So I take my statement back. If it's n or n plus 1 or n minus 1, we know that it alternates. If that's a power of -1. If it's anything else, you're going to have to actually think about it. So let's expand this one out. If n is 1, it'll be 1 times 2 divided by 2, which is 1. And -1 to the first is -1. So this will be -1 over 3 to the first. Okay. Then putting in 2. 2 times 3 divided by 2 is 3. -1 to the third is negative, so that'll be -1/9. You may be thinking, oh wait, that just means it's always negative. Why are you messing with this? Why are you making me work through all this? Please persevere. If n is 3, 3 times 4 divided by 2 is 6. And -1 to the 6th is +1, so this becomes +1 over 27. The one after that is +1 over 81. And then it continues. So this is not alternating. We cannot use the alternating series test. It has to strictly alternate to use that test. And it does not. Changed my mind halfway through. Not alternating. And I think I said does not alternate. Anyway, it's not alternating. So we cannot use the alternating series test. But what we can do, because we don't know anything about that thing's convergence, if it doesn't alternate but some. Remember what we did with that sine of n over n example? Of that expression that we were given for our series. We're going to take its absolute value, and that makes all the terms non-negative. Well, I guess it's, yeah, non-negative is right. Okay, so whatever -1's power is, you'll either get 1 or -1, and the absolute value of both of those is just 1. And 3 to the nth is already always positive, so the absolute value of that is 3 to the nth. And that's writable algebraically in this form. Which is a geometric series. Now, I knew that without expanding, because if you recall, the geometric series is of the form sigma a times r to the n or n minus 1, or whatever power it is. So this one is 1 times 1/3 to the nth. And so it takes on that character. And I can tell you that r is definitely 1/3. If I need a, I can find it by putting 1 in to find out what the first term is. I don't need a because I'm not finding the sum of that. We're just finding out if it converges or diverges. So, since the absolute value of that r is between 0 and 1, the sigma of the absolute value of our a sub n converges. And because of absolute convergence theorem, we know that it converges absolutely. Wait, let me back that up. I didn't say anything wrong, but I was writing it in the wrong place. So because the sigma of the absolute value converges, that means that sigma of a sub n, which was n equals 1 to infinity of -1 to the n times n plus 1 divided by 2 power all over 3 to the nth, that it converges absolutely. And if it converges absolutely, of course, that means it does converge. That's the definition of converges absolutely, is that it converges and sigma of the absolute value of it converges. So if we can find that it converges absolutely, then we know it converges. All right. So that answers that question for the first one. Next one. Going from n equals 1 to infinity, -1 divided by natural log. This is the one I started to write earlier. You may have been thinking, oh, wait, I saw that just now. It's because I messed up earlier. Okay, so -1 to the first is -1. 1 plus 1 is 2, so that would be natural log of 2. -1 squared is +1. Natural log of 2 plus 1 is natural log of 3. And of course this one is alternating. Write a few more terms if I want to. Kind of get that pattern established that it alternates. So we know that it's an alternating series. And we should be able, therefore, to identify what a sub n will be. Remember, that's the part that includes everything except for the power of -1. That's making it alternate. Okay, so since it's alternating, we have a two-part test. The first part of that test is, what is the limit as n approaches infinity of that a sub n? Function increases without bound as you go towards positive infinity. So if that denominator is increasing towards infinity, the fraction is going towards 0. Check. Number 2. A sub n plus 1, which is 1 over natural log of n plus 1 plus 1, or in other words, n plus 2. I'm substituting n plus 1 in for each n. And I want to compare that to our a sub n expression. Is that, which is of course a sub n. And since the natural log function is an increasing function, the natural log of n plus 2, which is further along to the right, will be bigger than the natural log of n plus 1. And since the left-hand denominator is bigger than the right-hand denominator, the fraction on the left is smaller than the fraction on the right, which is what we needed for it to be. So we can conclude from this alternating series test, therefore this series converges. So since we've established convergence, we need to find out if it converges absolutely or conditionally. We've got another big part of the problem to go. So when it converges, you then have to find if it's absolutely or conditionally convergent. The way to do that is to look at sigma of the absolute value of the expression of your series, -1 to the nth, divided by natural log of n plus 1. And simplifying that absolute value. By the way, I don't want you to skip writing the step with the absolute value because I need to see that you've done that, that's why that becomes this. Don't just jump to what I'm writing right now because I need to see that absolute value because that means you're entering into a certain kind of test. Okay, so let's see. I'm going to do some more magic here, mathematical magic. You might need to get a calculator to kind of follow along with my argument and see that it's true. I claim that the natural logarithm of n plus 1, so you might want to graph in your calculator y equals the natural log of x plus 1. And then in y2 put n. So we're going to compare those two graphs, natural log of x plus 1 and the graph of y equals x. And for n greater than or equal to 0, how do those two graphs compare? Look at the y values for n equals 0, n equals 1, n equals 2, because that's all that matters, are positive values of n. In every single case, the natural logarithm graph is less than or equal to n. So there's a true statement. Again, how did I come up with that? Like I did last time, I worked it the other way around, backwards from what I'm showing you now, and then reversed it to get this argument. So I'm going to take the reciprocal of both sides. Do you remember what that does to the inequality? When you take the reciprocal of both sides of the inequality? Yes, it changes the direction of the inequality. Okay, so that 1 over n is a series that I'm familiar with. Harmonic series is what? Always. It's divergent. It diverges. And what if the terms of our series, notice that I've produced on the left-hand side an expression of the absolute value of a sub n, that 1 over ln of n plus 1 that I have up there at the top right of what you can see right now. Since those terms are bigger than the terms of a divergent series, we can conclude, therefore, that the series that is the absolute value of our a sub n diverges. Why? What test did we use? We used direct comparison. You are going to need to know those names of those tests and know which one you're using when. So that's something to make sure that you're cognizant of all the time. Okay, so our final conclusion is that therefore the sigma of A sub n, which converged, converges conditionally above diverges. So when that happens, that sigma of A sub n converges and sigma of absolute value of A sub n diverges, that's called conditional convergence. So sigma of A sub n converges conditionally. Right. Rearrangement of series. A finite sum, like 1 plus 3 minus 2 plus 5 minus 4, can be rearranged without changing the value of the sum. So if you did 1 plus 3 plus 5 minus 2 minus 4, the answer is no different. This is not necessarily true of an infinite series. It depends on whether the series is absolutely convergent or conditionally convergent. So if the series is absolutely convergent, then its terms can be rearranged in any order and you will not change the sum. That's the one that's going to make you happy, because it's like those numbers that we added 1 plus 3 minus 2 plus 5 minus 4. In whatever order you add those, you always get the same answer. That's true. However, if the series is only conditionally convergent, then its terms can be rearranged to give a different sum. That's supposed to make you feel a little bit awkward. If I do 1 plus 2 plus 3, or add 1 plus 3 plus 2, and all of a sudden, of course, there's more stuff because it's an infinite series, but the rearrangement of those not giving the same answer should make us all feel kind of gross. And that's because it's a conditional convergence situation. So let's look at this one. This is negative 1 to the n plus 1 times 1 over n. Oh, that's a good friend of ours. That's the good old alternating harmonic series. And I'm going to give to you that someone has figured out what this one converges to for us, and they figured out that this converges to the natural logarithm of 2. Okay? So, let's rearrange the terms of this series and get a different sum. So, what if I were to rearrange them in this order? 1 minus 1/2, minus 1/4, plus 1/3, minus 1/6. Now you have to make sure you don't forget any of the terms as you write these down. And I'm writing a whole lot more of them than I did up above. So I would have written out a lot more of the terms to find out what these were. Okay, I'm almost to the point where I want to stop. I'm hoping you can see the pattern here, how I'm producing these in this order. There's a pattern to it. Okay. So, if I rearrange them in that order, then I could group those very selectively and say, well, I'm going to do 1 minus 1/2 minus that 4th. And then I'm going to group the next two together. That's 1/3 minus 1/6, and then minus a 4th. You see what I'm doing? Then the next one will be 1/5 minus 1/10 minus the 1/12 plus 1/7 minus 1/14 minus something, etc., etc., etc. Okay, so simplifying, that's 1/2 minus 1/4 1/3 minus 1/6 is how much? One-sixth is right. Minus 1/4. 1/5 minus 1/10 is 1/10 minus 1/12. 1/7 minus 1/14 is 1/7 minus something, etc. Then all of those denominators are even, and so I can, which leaves 1 minus 1/2 plus 1/3 Oh, I see. I made a mistake. Maybe you saw it faster than I did. This 1/8 up here, the 1, 2, 3, 4, 5, 6 thing, I wrote 1/4 there accidentally. That's a 1/8. And so this is a 1/8. My apologies, because I was about to have to write something that was false, and I don't want to do that. So that's minus 1/4 plus 1/5 minus 1/6 plus 1/7. Oops. Oh. Drat. 1/7 minus 1/14 is not 1/7. Having one of those days. 2/14 minus 1/14 is 1/14, not 1/7. That's a 1/14. And factor out the 1/2, and that leaves us 7 minus ... And what's in parentheses is the exact same thing as the original series. Look up there. What's inside parentheses is that. And so we were told that that is equal to natural log of 2, so that by substitution for that series with ln of 2, we found out that our series is sometimes equal to natural log of 2 and sometimes equal to 1/2 of natural log of 2. It's equal to both, depending on how you've arranged them. Ooh, that is not going to make you comfortable, but it's because it's conditionally convergent. That's how that's possible. All right, that ends this section. I'll see you in class.